The magnetic force of a magnet is caused by the spin of electrons. In an electromagnet, magnetic force is generated when an electric current flows through a coil, as shown in following figure. Electrons possessing an electric charge rotate along the coil to produce this force. Historically, it was proposed that the internal charge of an electron rotates due to its self-rotation, similar to an electromagnet. However, calculations showed that the rotation speed would need to exceed the speed of light, so this idea is currently rejected. In modern quantum mechanics, quantum spin is defined as the intrinsic angular momentum of a quantum. In our space theory, electron spin is explained by rotation vectors and their precession. Precession is the quantum spin itself. Furthermore, it is not the charge that rotates. Rather, the combination of the rotation vector and its precession constitutes the electric charge. In our space theory, a photon consists of rotation vectors, energies possessing three orthogonal rotational force components in the x, y, and z directions. When the photon's energy increases, e.g., during pair production, the rotation speed of these vectors increases, causing them to influence one another. As shown in following figure, the phase of each rotation vector collides with the rotational plane of the orthogonal vectors, acting to rotate those planes. For example, if we place the starting point of rotation vector x on the phase circle of rotation vector y, it forms a geometry like a hop-flink. First, rotation vector x rotates slightly along the phase circle of rotation vector y. Next, rotation vector y rotates slightly along the phase circle of rotation vector x. As this repeats, rotation vectors x and y orbit each other like binary stars while maintaining their orthogonal relationship. This orbital motion is the precession. Since the vectors are orthogonal, the precession angle is 45 degrees relative to the central axis of rotation. Rotation vector z then pairs with the orbital phase of the xy pair and precesses at a 45-degree angle. While size, in the conventional sense, does not exist in our space, if we treat the rotation vector as angular momentum and the radius of the phase circle as the arm length, radius 1, the arms of x and y are divided into two relative to the orbital axis, making each length 1/2. Since angular momentum, kilogram times meter square per second, is proportional to the square of the length, the four arms, 2 from x, 2 from y, of length 1/2 each have an angular momentum of 1/2 squared equals 1/4. The total angular momentum of these four arms equals 1, which balances with the angular momentum of rotation vector z, which is 1. Alternatively, calculating as vectors, x and y are tilted at 45 degrees to the precession axis, making their arrow lengths in the orbital plane 1 divided by the square root of 2 each. Squaring these gives 1/2 each. Combined, they equal 1, balancing with vector z. These precessing rotation vectors are electrons and quarks, and the invariance of the speed of light is due to this fixed 45-degree precession angle. In our space, electric charge is explained as a combination of rotation vector inversions. An inversion is a 180-degree rotation of direction. One 180-degree rotation causes repulsion, while two such rotations, returning to the original direction, result in attraction. Electrons consist of 3 rotation vectors. In contrast, as explained in later chapters, an up quark has only 2 rotation vectors because one component is confined. When two electrons interact, their x, y, and z phases collide and move apart, resulting in repulsion. Similarly, two up quarks experience repulsion as their x and y phases collide. However, in an electron-up quark interaction, the electron's x and y phases collide and repel, but its z vector has no counterpart in the up quark. Consequently, the electron's remaining z vector pairs with the up quark's 2-vector pair, causing them to orbit together. Because the z vector has only half the force required to rotate the entire system, it causes a 180-degree rotation inversion. This adds an extra inversion to the x and y components, totaling 2 inversions, which causes the phases to approach each other. This is the attractive force. Given that rotation vectors represent angular momentum, the relationship between the number of rotation vectors, n, and the charge, q, is equal to -1 raised to the power n times n divided by 3. An electron consists of a pair of 2 rotation vectors and 1 single rotation vector orbiting each other. Based on the charge formula, this is equivalent to a positive 2/3 charge and a negative 1/3 charge orbiting each other, which generates magnetic force like a microscopic electromagnet. However, the electron as a whole has a charge of -1, calculated via inversions, not simple addition. Furthermore, magnetic force is not emitted. Rather, electrons interact with each other. When the spin axes and rotation directions of 2 electrons align, the precession of the partner appears to have only 2 components, x and y, due to synchronization, much like how a car moving at the same speed appears stationary. From each electron's perspective, it sees itself as having 3 vectors and the other as having 2, causing their phases to approach each other. In our world, this is perceived as magnetic attraction. In summary, spin, charge, and magnetism all originate from rotation vectors and their precession.